My name is Session2-1, and today I will present the results on
our collaborative project devoted to current-driven plasmon instabilities in graphene heterostructures. Before starting, I would like to thank Professor Ono for giving us the possibility to hold this collaborative research with the group of Akira Sato here in Tohoku University and with the laboratory of Professor Keiichi Kotsuchi. And the outline of my talk is the following. First of all, I will tell you about how the plasmonics can help us in principle to bridge the terahertz gap. The main part of my talk will be devoted to the methods of plasmon generation in graphene, and I will cover three such methods. The first one is the generation of plasmons exploiting resonant tunneling. The second one is generation of plasmon in excited graphene with population inversion. And the third part is current-driven instabilities or generation of plasmons by direct current. Finally, I will draw some conclusions. First of all, I would like to tell that detectors and generators of electromagnetic radiation in the terahertz range are highly demanded by society due to the medical applications, security applications, and data transfer applications. And each terahertz conference actually starts with this picture of terahertz gap, which show that the power of electromagnetic generators goes rapidly down when approaching the frequencies from 1 to 10 terahertz. And this is related to both devices using radio engineering principles and to the lasers. Actually, this picture is quite old, and during the last 10 years, there was a considerable progress in filling this terahertz gap. For example, in the left side of this terahertz gap, the devices using vacuum tube principles perform quite well and deliver high power of terahertz radiation. Still, they require very large drive voltages, order of several kilovolts. In the left end of the terahertz gap, there are also some low power devices which are very compact, and these are resonant tunneling diodes. But their output power still remains very low, order of several microvolts. In the right-hand side of the terahertz gap, the best devices currently are quantum cascade lasers, which deliver coherent electromagnetic radiation with power order of 1 milliwatt. But their operating temperatures are currently quite low, they are only cryogenic. And so, despite the recent advances in terahertz technology, there appears a lot of space in this terahertz gap to be filled with new devices. But before designing these new devices, we should first answer the fundamental question, why the efficiency of terahertz generation is low for most semiconductor devices. One of the problems is the huge size mismatch between typical semiconductor devices and terahertz wavelengths. The typical semiconductor device, which is a diode or transistor, is typically small. Its size is below 1 micron, and the wavelength of terahertz radiation is 300 microns. And this size mismatch between terahertz wavelength and device size makes the interaction of semiconductors with terahertz waves very inefficient. And we might think about coping with these problems by shrinking the electromagnetic energy to a very small scale up to the device scale. So we want to shrink the electromagnetic energy down to the scale of several microns to make the interaction of electrons in semiconductors with light much more efficient. From the first side, one may think that it is impossible because it's impossible to shrink light to the distance smaller than the wavelength. But indeed, it is possible, because there are special types of electromagnetic waves which are called surface plasmids, which are highly confined to the interfaces between conductive surfaces and dielectrics. And plasmons are indeed highly localized oscillation. They are localized at the distance much smaller than the wavelength of light in free space. And the interaction of electrons in semiconductors with these surface plasmons is very efficient. So terahertz plasmons can act as efficient mediators for the generation of electromagnetic waves by semiconductor devices. Actually, these surface plasmas already find a lot of applications. The most well-known applications are for resonant photodetection, for plasma enhanced biosensing. One of the most interesting proposals is using the surface plasmas for on-chip interconnects and data transfers. But still, the main applications of plasmonics is the design of terahertz emitters. It appears that electric current in a field effect transistor is in some sense similar to the flow of water in the rivers or to flow of air in the music instruments, and the phenomena similar to wave generation and turbulence that we saw in conventional water and gas flows can also appear in semiconductors. So at certain conditions, the flow of current in semiconductor can become unstable and break down into plasma waves. And as these waves are charged, they produce electromagnetic radiation. And therefore, such devices with plasma instabilities are sometimes called electronic fluids. Actually, the first prototypes of these electronic fluids were fabricated and measured here in Tohoku University, and they are based on the two-dimensional electron systems in 3-5 semiconductors. The current project was devoted to the plasma instabilities and plasma generation in a novel semiconductor, which is graphene. And I will cover 3 such methods of plasma generation. The first one exploits the phenomenon of resonant tunneling, where an electron traversing from between 2 parallel graphene layers can lose its energy by emission of surface plasmon. The second method will deal with highly non-equilibrium graphene, where a large number of electrons and holes is present, and these electrons and holes can recombine in the emission of surface plasma. And finally, the third method and the main method will deal with current-driven instabilities, where a direct current passing through graphene samples is converted into plasma oscillations. Well, let's start from the first method of resonant tunneling. The structure under consideration corresponds of 2 graphene layers separated by a thin tunnel barrier. These structures are actively investigated and they are promising for non-electronic applications as field effect transistors. And their IV curves demonstrate a resonance in current followed by negative differential resistance region. And this resonant peak is associated with the fact that at some voltage, the direct tunneling of electrons from one layer to another becomes energetically possible. Actually, a closer inspection of these devices shows a very interesting fact that these devices not only demonstrate resonant peak in current, but they also demonstrate terahertz emission, which is highly controllable by the gate voltage. And these devices not only exhibit resonant tunneling, but also emit terahertz waves. And one possible scenario of this emission is the following. An electron can tunnel from one layer of graphene to another and emit an excess of energy and momentum by a surface plasma. And later, this surface plasma can decay into free space photon due to some radiative processes. In this project, we have developed a theory of this resonant tunneling process with emission of plasma to see the ultimate capability of this process to produce plasmons. We have shown that under specific bias voltages, there exists a resonance in plasmon generation rate, and this resonance is unique to graphene due to its linear band structure, and it is absent in 3-5 semiconductors with parabolic bands. We have also investigated the methods to couple these plasmons to free space radiation, and we have shown that these plasmons can decay either by simple dipole emission, or they can be coupled to free space radiation by connecting the tunneling device with nanoscale antenna. And in both cases, the radiative decay rate of plasmons can be comparable to the scattering rate, which means that these plasmons can be efficiently converted into free space photons, and therefore such devices can be used as nanoscale sources of terahertz waves. The second method of plasma generation we have considered here is deals with highly non-equilibrium graphene with interband population inversion, which is a typical situation for semiconductor lasers. Actually, in equilibrium state, graphene, as any normal semiconductor, absorbs electromagnetic radiation, either by conventional Joule absorption or by interband absorption. But if one creates a population inversion between conduction and valence bands in graphene, then for certain frequencies, graphene can emit electromagnetic waves, both photons and plasmons. In the previous, on the previous stages of this collaborative research, we have calculated the conductivity or the dynamic conductivity of graphene under these non-equilibrium conditions and shown that it can be negative at several frequency ranges. And this negative conductivity can give rise to amplification of electromagnetic waves and particularly plasmons, which and therefore the absorption coefficient of plasmons can switch from positive to negative in the terahertz frequency range. In the current project, we have focused on the fact that it is actually very difficult to hold this inverted state for a long time, because there are some non-radiative recombination processes that aggressively compete with the favorable process of recombination via plasma or photon emission. The most aggressive competitor of this process is the process of non-radiative Auger recombination, where an electron and a hole in non-equilibrium state can recombine by transferring an energy to a carrier passing by. And the experiments on pump probe spectroscopy show that actually this non-radiative channel is quite strong, and the population inversion in graphene dies out in roughly hundreds of femtoseconds. In the current project, we have developed a method how to calculate these non-radiative recombination rates and how can we tune it to larger values. This developed method is based on non-equilibrium green function technique, which is quite complicated but still necessary in this problem because we need to account for a tiny renormalization of linear bands in graphene. And the results of our calculations show some interesting facts. For example, the Auger recombination rate is naturally strongly dependent on temperature, and it rapidly goes up with increasing the temperature. That means that recombination rate extracted from experiments on pump probe spectroscopy with hot carriers are much more pessimistic than recombination rates at real room temperature. And there is some possibility to tune these recombination rates by choosing different substrates for graphene and therefore tuning the dielectric constant of environment. This method of suppression, the recombination has limited capability. There are some more efficient methods to suppress non-radiative recombination. One of the most efficient of them is by introducing a metal gate near graphene. And by placing a metal gate closer and closer, one can increase the lifetime of non-equilibrium carriers by roughly an order of magnitude due to enhanced screening of column interaction. Another efficient method is to introduce a band gap in graphene, which would lead to an exponential enhancement of non-radiative recombination time. But with this method, one should be careful because to generate terahertz waves, this band gap shouldn't exceed several MeVs. Therefore, the results of our project indicate that in optimized graphene-based structures, the non-radiative recombination lifetime can be of the same order of magnitude as the radiative recombination lifetimes with the emission of surface plasmons. And this opens up large perspectives for non-equilibrium graphene-based terahertz sources. Frankly speaking, the previous two types of plasmon generation require quite exotic setups. And the most natural way to generate plasmons in graphene is to pass direct current under the conditions where it breaks down into plasma oscillations. And the scenario of such so-called current-driven instability is the following. a uniform drift of electrons with some uniform drift velocity and carrier density under some condition becomes unstable due to fluctuations of self-consistent electromagnetic field. And this uniform current pattern can transform into drift superimposed with plasma oscillations, which is called current-driven plasma instability. Of course, this situation, the instability of current, doesn't occur at any time. Otherwise, any current would be unstable. It requires very specific conditions, and we have revealed several types of conditions which can be realized in graphene-based devices. The first type of this situation is when these electrons constituting an drifting current have very collimated velocities, so when their momenta point to the same direction. This situation is called beam instability. The formation of electronic beams in graphene can be conveniently done with graphene-based p-n junction. In graphene-based p-n junction, due to Klein tunneling phenomenon, only the electrons incident on p-n junction normally can be transmitted forward, while the electrons with oblique angles of propagation are reflected back. And therefore, as a result of junction filtering, a very well collimated electron beam with narrow angle distribution is formed. And we have studied the stability of such a non-equilibrium configuration when you have large steady electron density in graphene superimposed with electron beam. For this purpose, we have calculated the loss function of graphene, whose peaks demonstrate the plasmons existing in the system as a function of energy and wave vector. And when you inject non-equilibrium electrons, extra plasmonic peaks appear in this system, which are called beam plasmon modes. And with increasing the beam density, there appears a plasmon mode which finally becomes unstable and breaks down into plasma oscillations. The growth rate of these oscillations has a maximum as a function of wave vector and direction of propagation, and we can estimate the growth rate of such beam instability and find the maximum growth rate. The maximum growth rate is actually an almost linear function of density of electrons injected in a beam. And under optimum conditions, it can reach several MeVs. This growth rate of instability actually exceeds the loss rate, which is due to electron-electron scattering and destruction of a beam due to carrier-carrier interactions, which mean that these beam instabilities can be realized in real graphene-based beam junctions. Another interesting method of generating plasmons which doesn't require these collimation of electrons deals with bilayer graphene-based heterostructures. One of the layers should be made of graphene, and the other layer should be made of two-dimensional semiconductor with parabolic bands. When you pass current in opposite directions in this setup, this double current system can again become unstable due to the excitation of plasmons. And this compound system supports two plasma modes. One is coupled to graphene, and the other one is coupled to the two-dimensional semiconductor. And the lower plasmonic mode becomes unstable at a large drift current. We have calculated the growth rate of such an instability as a function of two Fermi energies in graphene and massive two-dimensional electron gas, and revealed that at realistic drift velocities, order of 0.3 of Fermi velocity, this configuration becomes unstable, giving rise to a current-driven instability. Well, to conclude my speech, I would like to repeat that we have studied the methods to electrically generate plasmons in graphene for novel terahertz sources. We have studied three methods of plasmon generation. One of them uses the phenomenon of resonant tunneling in graphene-based tunnel junctions. The other one uses beam instabilities in graphene p-n junctions, and the third one uses two-stream instabilities in bilayer systems. We have also studied the generation of plasmons in highly non-equilibrium graphene-based systems and designed the methods to suppress non-radiative processes in non-equilibrium graphene. If you are interested in more detail about the results of this research, they are published. One of them is currently under review in PhysRev B and got positive reviewer comments, now available on arXiv. And the other paper on current-driven instabilities is currently under preparation. Thank you for attention.